to Team Mechanek. My name is Brahm, and along with my teammates Mark, Chris, and Anthony, we are presenting our finalist submission for the Intel-Cornell Cup. We're presenting an active head and neck brace for automotive racing. Currently, we are being advised by Dr. Matthew Maltese, the head of biomechanics research at the Children's Hospital of Philadelphia, and Dr. Andrew Jackson, professor of practice in mechanical engineering at the University of Pennsylvania. The Hans device was invented in 1983 by Dr. Robert Hubbard following the death of one of his close friends in an automotive racing accident due to basal skull fracture. The use of the Hans device was largely ignored through the late 90s until the deaths of several famous racing drivers such as Senna and Dale Earnhardt Sr., who died of basal skull fracture as well. The FIA and SFI began pushing the use of the Hans device and other safety equipment in order to prevent against basal skull fracture. Basal skull fracture is a fracture of the base of the skull that occurs in high-speed frontal accidents. As you can see in the top video, the head rotates through the full range of motion, whereas in the bottom video, the head is stopped before reaching the limit of the neck's range of motion. What occurs is when the head rotates to the limit of its range of motion and attempts to continue moving, the base of the skull, including the temporal and occipital bones, fracture and can actually sever the spine, causing instantaneous death.
Still, the Hans device is not perfect. Its main principles of operations have not changed much since being developed in 1983, so we saw a few different areas for improvement. The first one is that the head impact criterion is higher for drivers that wearing a Hans device. The HIC is a measure of the likelihood of head injury from a crash. While the risk of basal skull fracture is drastically reduced using a Hans device, the risk of concussion and other mild traumatic brain injuries are increased. The second problem we identify with the Hans device is that it severely limits the driver's range of motion and field of view. This has led to a lot of pushback from drivers from both professional and amateur skill levels. The last problem that we identify with the Hans device is that it's completely passive. Modern cars have hundreds of sensors that provide useful data for predicting crashes. We felt that we could use this data to proactively restrain the driver, which the Hans device currently cannot do.
So, to counter the drawbacks of the Hans device, we came up with 3 goals for Mechanek. The first goal is to lower the risk of basilar skull fracture and the risk of mild traumatic brain injury. The second goal we have for Mechanek is to not restrict the range of motion for the driver at all. And then the last goal we have is to interface with existing crash detection technology in cars to successfully predict and proactively respond to crashes. So to solve the 3 problems I just discussed, we came up with this device. Mechanek interfaces with existing Hans devices and replaces the 2 static tethers with 2 actuated tethers that move with the driver's head. Now I'm going to discuss the mechanical subsystems in a little bit more detail. The first subsystem that I'm going to talk about is the tether tension control system. This is the system that keeps the tethers taut and moves with the driver's head as he moves around to see different parts of the track. So there are 2 main components in the tether tension control system. The first is a pair of Maxon DC motors. These DC motors interface with 2 aluminum spools. The tethers are mounted around those spools, and we can roll up or roll out the tethers as needed to move with the driver. The second critical subsystem is the tether locking mechanism. The subsystem I spoke of earlier, that's what allows the driver's head to move without obstruction. But in the case of a crash, we need to lock the tethers in their place to avoid basal skull fracture. So the tether locking mechanism starts with 2 LEDX linear solenoids. Those solenoids are attached to a cam, and that cam holds back 2 stainless steel pawls. When the solenoid rotates the cam, the pawls are allowed to interface with 2 ratchets on either side of the spool. When the pawls spring forward, they lock in place with the ratchets and prevent the spools from letting out any more tether. Of course, all the mechanical subsystems need electronics to control them, and that's where this control box comes in. It will be mounted under the driver's seat or maybe even behind the seat, and it allows data to come in from the car and data to be output to the motors and solenoids that I just discussed. Of course, it's what's on the inside that's really important here. The electronics can be split up into 3 different purposes. The first set of electronics are responsible for sensing. There's an onboard 200G accelerometer that's constantly monitoring for crashes. There's also an onboard 16G accelerometer that we set to look for acceleration peaks over a certain threshold. If it sees acceleration peaks over a certain threshold, it indicates that there's probably a crash occurring. The last component in the sensing side is the OBD2 data port. That brings in vehicle diagnostic data such as wheel slip, brake position, throttle position, airbag deployment sensors, and we can look at all that data and analyze it and determine if a crash is occurring from that information. The second component of the electronics is the computation component. This is where the Intel Edison comes in. The Intel Edison takes all the data coming in from the sensors and processes it, and it also is responsible for the actuation. On the actuation side, we have the two solenoids that I discussed earlier. They're responsible for locking the tethers. We also have the two motors that are responsible for spooling in and out to keep the tether tension taut.
After we developed the Mechanek system, we needed an efficient way to test and validate its effectiveness. For our validation, we based our tests on what's known as SFI 38.1, a series of specifications that outlines the crash testing necessary to test head and neck restraint devices. To conduct these tests, we went to Buffalo, New York at Calspan Corporation, a high-tech crash test facility. They allowed us to perform two tests, one control test with a Hans device and a second comparison test with our own Mechanek system. Each of these tests was a 35 mile per hour velocity change and a 40G pulse. This replicates the tests conducted by Hans at Wayne State University when the Hans was first being developed. For each of these crash tests, we utilize what's known as an ATD, or anthropomorphic testing device. These are crash test dummies that are fully instrumented to allow us to have live feedback of data from the crash test dummy itself. Here we have two plots of our data from these crash tests. The top plot shows the resultant head acceleration, and the bottom plot shows the neck injury criterion. In this case, we're showing one component of the neck injury criterion known as tension flexion. Simply looking at these plots, we can see that Mechanek has decreased these peak values by a significant amount. But what does this value actually mean? Looking at the data more closely, we see that Hans has a HIC of approximately 642, while Mechanek decreases this by approximately 28% to 464. NHTSA dictates that a value of 700 in an HIC means that there is a high risk of mild traumatic brain injury. Moving this away from the high threshold means that we have created a more effective head and neck restraint device. Next, we can look at the NIJ, or the neck injury criterion. Hans has a value of 0.66, while Mechanek has a value of 0.53. The neck injury criterion is a normalized criterion that describes the injury risk of the human neck. This value is calculated with a combination of the axial loading and bending moments. The next goal of Mechanek was to reduce the restriction placed on the driver's head when wearing a head and neck restraint. We can see in these videos that the Hans device has an extremely limited view of approximately 90 degrees. Mechanek, when implementing its active tether system, can increase this field of view to almost 150 degrees. In summary, this is what our team has managed to achieve. Mechanek performs better than the Hans device on critical measures of head and neck injury risk by 20 to 30%. Mechanek also offers drivers a full field of view, helping them avoid crashes in the first place. Mechanek interfaces with onboard vehicle diagnostics in order to predict and proactively respond to crashes to keep drivers safe.
In closing, we'd like to thank all of our sponsors, especially the Intel-Cornell Cup, for giving us this opportunity.